Marcello Porta, who is now at Tübingen, and he will speak on two-dimensional topological insulators.
Thank you, Manfred, for the introduction, and thank you very much for the invitation. It's a great pleasure to be here at this very nice this workshop and at this thematic period. So today I would like to talk about some topics motivated by condensed matter physics, and in particular about some application of the renormalization group to studying transport for actually more precisely edge transport for two-dimensional quantum systems. What you will hear is based on a joint work with Giovanni Antinucci from Zurich, who is here in the audience, and Vieri Mastropietro in Milan. All right, so let me start. So this is a summary of what I would like to talk about. I will first make an introduction about the kind of physical problems I would like to discuss, namely edge transport in topological insulators, and more precisely I will focus on quantum Hall systems and time reversal invariant systems. Okay, so I would like to start by discussing some known results about non-interacting models, about bulk and edge transport actually, and I would like to highlight a well-known and remarkable duality between bulk and edge transport, which takes the name of bulk-edge duality. The main part of this talk, and that's where I will present results, is about the extension of some of these predictions to the many-body world, so interacting fermions. And the main results I will present are about a theorem about the computation of edge transport coefficients for quantum Hall systems, or for a class of quantum Hall systems and time reversal invariant systems. So as a direct application of this theorem, which gives a pretty nice characterization of edge transport, we will get we will get a proof of the bulk edge correspondence for interacting fermions for a suitable class of models, and we will also get a statement about a non-trivial relation between some suitable edge transport coefficients, Drude weights and susceptibilities, and this relation between Drude weights and susceptibilities takes the name of Haldane relation, and we're going to show that this relation holds true for this class of edge transport problems. The proof of the theorems I will present are based on rigorous renormalization group techniques for interacting fermions, and universality, and all the universality properties of these edge transport coefficients are going to follow from suitable use of word identities, which follow from conservation laws. All right, and then I will conclude and perhaps discuss some open problems. So let me start by giving an introduction about the physical problem for non-interacting systems. Okay, so it is very well known by now that bulk transport, which is associated to some bulk topological order in condensed matter systems, is deeply related to the presence of gapless edge modes. Okay, so which naturally appear whenever your sample terminates. Okay, and so perhaps to explain this a little bit, let me start from the simplest possible, perhaps the most well-known example of topological insulator in two dimension, namely, the integer quantum Hall systems, and that's going to be about the integer quantum Hall effect. Okay, so the setting is the following: you have a very thin sample of a suitable material. You might think of it as being two-dimensional, at least schematically. And what you want to do, you want to expose this two-dimensional system to a transverse magnetic field, as in this picture here. And not only this, you also want to expose your material to a weak in-plane electric field, which in this picture is directed along this axis. Okay, so because of this setting, what you're going to expect is that the electric field is going to drive charge carriers along the plane of where your material is defined, but also the magnetic field is going to produce an accumulation of opposite charges on the sides of this slab. That's just because of the Lorentz force. Now, if the application of the external electric field is weak enough, then what you expect from physics is that there will be a current developing on the surface of your material, which is going to be linear in the applied field. That's just linear response theory. Okay, and the matrix, the 2x2 matrix that gives you the current, which is a two-component current, because we're talking about two-dimensional system, the matrix that gives you the current as a function of the applied electric field at first order is the so-called conductivity matrix. It's just a 2x2 matrix. Okay, so the integer quantum Hall effect is a statement about the structure of this conductivity matrix, and well, it says that in suitable experimental conditions, very low temperature and very strong magnetic fields, the diagonal part of this conductivity matrix is exactly 0, so no longitudinal conductivity at all, while the transverse, the off-diagonal part of this matrix, namely the transverse or Hall conductivity, is exactly quantized. Okay, so here you see a sketch of, actually these are experimental data for realistic quantum Hall systems. Actually, what you really measure is not the conductivity matrix, but rather the resistivity matrix, so that's the inverse of the conductivity matrix. And what you see here is just, this series of sharply quantized plateaus is the series for the Hall resistivity. And in corresponding, the other interesting part of this picture is about the spikes that the longitudinal conductivity takes whenever you are at the transition between two different plateaus. Okay, so when you are in the plateau as a function of the magnetic field, the longitudinal conductivity is 0 while the transverse conductivity is quantized. When you move from one plateau to another, you see a spike in the longitudinal resistivity, which otherwise is exactly 0. Okay, so this is a purely quantum phenomenon. If you try to make a prediction about let's say the transverse conductivity starting from the laws of classical electrodynamics, what you would observe is that the transverse conductivity should be a linear function of the density of charge carriers, and B is related to the density of charge carriers. So this is a really macroscopic quantum phenomenon. All right, so what about the theory or the explanation for this phenomenon for non-interacting fermions? Okay, so if you have a system of non-interacting fermions, the model is defined by a one-particle Hamiltonian, namely Schrödinger operator acting on an infinite two-dimensional lattice, on L2 of the infinite two-dimensional lattice, and you might also want to include some internal degrees of freedom, let's say the spin or sublattice degrees of freedom, and so on. Okay, so the relevant setting for quantum Hall physics is to assume that the spectrum of this Schrödinger operator is gapped. Okay, so this is a possibility. You might have a certain number of disjoint bands, and then you have a region of the spectrum, a region of the real axis where there is no spectrum at all. You might have other bands here, and you want to place your Fermi level in this gap. That means that at 0 temperature, all the single particle states that are going to be occupied are all the states that have energies less than the Fermi level mu. Okay, so if you have a finite lattice, what really happens is that the many-body ground state of your non-interacting system is just a Slater determinant that you get by filling up all the single particle level here. If you have an infinite lattice, the state is described by what is called the Fermi projector. That's an infinite rank operator which projects over all the, over the portion of the spectrum that is below this Fermi level mu. So for simplicity, let me consider the case in which we are translation invariant. That means that H, the integral kernel of H, is actually just a function of x minus y. These are 2 points on the lattice. And if so, let me diagonalize H in the basis of, in terms of the plane waves, right? So this is just Fourier transform. I'm taking the Fourier transform with respect to plane waves, and in this way, if I do that, I introduce this matrix, actually, H hat of k, which is the so-called block Hamiltonian. Okay, so that's the Hamiltonian as a function of momentum k, which is a point on the two-dimensional torus, and this turns out to be just a matrix, and this matrix is what one calls the block Hamiltonian. Okay, so once you are given this block Hamiltonian, you can introduce the Fermi projector as a function of k, which is just the characteristic function of h being smaller than the Fermi level mu. All right. And just in terms of these ingredients, you can try to compute the transverse conductivity starting from just linear response theory. So you take the average of the current operator, you expose it to an external weak and slowly varying external electric field, and you just do first order expansion in Duhamel series in terms of the electric field. Okay, so you just expand the average of the current operator as a function of the electric field. You do that at first order, and what you notice is that at first order, the transverse conductivity is given by this nice integral here, which only depends on the Fermi projector P. Okay, so that was an observation of Thouless and collaborators at the beginning of the 80s. And the nice thing about this expression is that it explains quantization of the transverse conductivity via topology, because this integral here turns out to be related to a suitable topological invariant, namely the Chern number of a suitable bundle, which is called the block bundle, which is defined here. So it's a bundle which has the two-dimensional torus as base space, and the fibers are just the range of the Fermi projector. So that's for the simplest case of translation invariant systems. Then starting from that, people understood the quantum Hall effect in more general settings, also from a mathematical viewpoint, and here I'm just mentioning some important works in this business. All right, so this is about bulk transport properties. However, what I promised is that this talk is going to be about edge transport properties. So let me tell you what is the phenomenon that one would like to explain here. Well, this is so the relation between bulk and edge transport properties for quantum Hall systems was first somehow proposed by Halperin at the beginning of the 80s. So what Halperin predicted is that whenever you have a non-trivial, if you're able to measure a non-trivial bulk Hall conductivity for your physical two-dimensional system, this has to come with stable edge currents propagating on the edges. Okay, so that's somehow summarized by this picture here. Suppose that you have a two-dimensional system that is somehow confined to live on this annular geometry. Then suppose that you have a magnetic field that comes out of the screen, and suppose that you're able to measure deep inside your sample. Suppose you're able to measure a non-trivial Hall conductivity. Okay, so this necessarily has to come with stable edge currents that propagate on the two edges of this ring. So, all right, so there are by now a few ways to understand that, but perhaps a very nice way is by using a field theoretic approach. Okay, so think about the partition function of rather generating function of connected correlation functions for your non-interacting Fermi gas in the presence of an external U1 gauge field. So it turns out that if you assume that your interacting Fermi gas has a gap, so the ground state of the system is separated by the rest of the spectrum by a positive gap, then you can compute explicitly somehow as a series the effective action of your non-interacting theory as a function of the external gauge field A and as a function of the derivatives of the external field A. And by symmetry reason, so if you scale out, I mean, you choose this A to be weak and to be slowly varying, so you have to introduce a scaling parameter in that. But if you do that, at leading order in the scaling parameter, you see that by symmetry reasons, the only, I mean, the term, so let's say the only term that is not vanishing as the scaling parameter goes to 0 is this abelian Chern-Simons term. Okay, so you're integrating over this region omega, which actually turns out to be given by a space-time region. It's the product of a time direction times the space direction, which is in this case is a ring of this suitable object here. Okay, so that's the scaling limit of the effective action. Now, I mean, we know that fundamental principle of coupling external electromagnetic fields with matter is that they have to satisfy U1 gauge symmetry. So let's try to do a U1 gauge transformation. That means that you replace the external potential A by A plus the gradient of some function alpha that defines a U1 gauge transformation. And then what you do next, you just apply Stokes' theorem, right? So if you do that, you just reconstruct what you had at the beginning, so A wedge dA. But then you also have a term which, if you apply Stokes, it boils down to an integral of some, an integral that only lives on the boundary of this region omega. Okay, so there is an apparent contradiction, because you see that we started from this guy. What we would have is, what we actually would like to prove is that this object is invariant under local gauge transformations, but we're not finding that. I mean, we're finding a non-trivial phase factor here, which is spoiling gauge symmetry. Okay, so since we know that, gauge invariance is a principle of fundamental principle of nature, and Stokes' theorem is also correct, the only thing that might go wrong is this gap assumption here. So this was an underlying assumption under this expansion in terms of A and derivatives of A, and that cannot be true. Okay, so if you have a non-zero Hall conductivity, that has to imply that the gap assumption cannot be true, and that was pointed out already in the early 90s by Jürg Fröhlich and collaborators. All right, so let me be a bit more precise, and in particular, let me come back to lattice Schrödinger operators. So let me consider a Schrödinger operator H that is defined on a cylinder. All right, so you should think of this square to be filled by lattice points, and then I would like to identify this side of the lattice, this side of the square with this one. So that's really a cylinder, and I want to impose Dirichlet boundary conditions on these dotted lines. All right. So together with this operator H, let me also consider the operator HP, which is actually the counterpart of H with periodic boundary conditions in all directions. Okay, so not just on this vertical side, but also above. And let me assume that HP, the periodic operator, is get for all sizes of the system. So in particular, if you take the limit as L goes to infinity, you want to have a Hamiltonian that describes an insulator. So you have a band gap at the Fermi level. All right, so that's about HP, but of course we know that the spectrum of H might differ from the spectrum of HP because of the non-trivial boundary conditions, and that's what might happen. So this is basically encoded in this picture here that I'm going to explain in a moment. So let me suppose that my operator H is translation invariant in the direction where I have the periodic boundary condition. So that means that I can do a partial diagonalization in terms of plane waves in the direction in the horizontal direction. And if I do that, I get this family of effective one-dimensional Schrödinger operators H hat of K1. Okay, so these are one-dimensional Schrödinger operators which are parametrized by a momentum K1, which is a point on the circle. And then you can ask, what is the spectrum of these operators as a function of K1? And that's basically what you see here. So you fix K1, you look up, and you see bands. These gray bands would actually be related to the essential part of the spectrum of the Hamiltonian without any boundary. But on top of it, you might have eigenvalues, which as a function of K1 describe curves. Okay, so these eigenvalues, they actually close the gap, right? So for a given K1, you have an eigenvalue, but as K1 varies, you might have that this eigenvalue actually draws a curve that connects the two gray bands. Okay, so that's the edge state corresponding to one edge of your cylinder. You might have another one by symmetry reasons on the opposite side. That's the blue dotted curve. Okay, so mathematically, these eigenvalues, they correspond to, these are eigenvalue branches parameterized by K1, and they correspond to eigenstates of your Hamiltonian H, which have the following form. I mean, they're just a plane wave on the one direction, the translation invariant one, and an exponentially decreasing function in the bulk. Okay, so these are the states that are responsible for transport on the edges. Okay, so that's how the spectrum might look like, and the bulk edge duality for quantum Hall systems is an interesting, is a deep statement between two different models. If you want, it's about the transverse conductivity for your model without any edges in the infinite volume limit, which is quantized by what I was telling you before, and the sum of the so-called chiralities of the edge states once you introduce an edge in your sample. Okay, so these omega e plus minus ones, these are just related to the sign of the velocity of the edge states. Right? So think about this picture here. What do you have? Well, forget about the dotted blue curve. This is, suppose that you just have one edge. The other edge is lost at infinity. So in this situation, the velocity is positive. That means that the chirality is plus 1. So the whole conductivity is 1 over 2 pi. In this other case, the velocity is negative. That means that by this formula, the whole conductivity is minus 1 over 2 pi. In this situation, you have no edge states at all. That means that the whole conductivity is 0. Okay, so that is something that has been proven at a mathematical, as a mathematical theorem. The first rigorous result was given by Hatsugai at the beginning of the 90s for its translation invariant systems, and then this has been extended to a larger setting of non-interacting Fermi gases, also including disorder, and in particular also including the so-called Anderson localization regime, where you have pure point spectrum and not a band gap. Oh, okay. So that is about systems where it's about quantum Hall systems where a magnetic field is breaking time reversal symmetry. So by now we call we know that quantum Hall systems are an example of topological insulators. So these are material where transport can be, quantization of transport can be explained via topological ideas that somehow mathematically allow to classify Schrödinger operators in terms of suitable topological invariants. In the previous case, the topological invariant was the whole conductivity, or the Cher number for translation invariant systems. Now the question is, what happens if you have, what happens, for instance, if you don't break time reversal symmetry by an external magnetic field? Okay, so if you want to have a non-trivial whole conductivity, the magnetic field is crucial. If you don't have that, you can prove that you cannot have any non-trivial charge transport. So what you can have if you don't break time reversal symmetry is, you will not have charge transport, but you might have a non-trivial spin transport, and that is summarized by this picture here. So think about a system that has two edges, and by time reversal symmetry, it follows that you cannot have a net charge transport, because if you would apply time reversal symmetry, the charge would just flip direction, and you would get this other charge current here. But the point is that time reversal symmetry also flips the spin. Okay, so you don't have any net charge transport on one edge, but you might have, you will have actually a net spin transport. That's what you would observe here. Okay, so that is called the quantum spin-Hall effect, which, I mean, that's an interesting topological spin transfer phenomenon, which was actually measured by now 10 years ago in real experiments. Okay, so what about, again, the theory for this phenomenon for non-interacting fermions? Let me consider a gapped time reversal invariant Schrödinger operator on a cylinder as before. And let me again suppose that I have translation invariance in one direction, where I have periodic boundary conditions, so I can introduce again this family of one-dimensional Schrödinger operators parameterized by K1. And by time reversal symmetry, you know that h hat of K1 has to be related to the time reversed h hat of minus K1, where theta is the map that implements time reversal symmetry for fermions, which turns out to be given by an anti-unitary operator which squares minus 1. Okay, so that's the time reversal symmetry for fermions. And the nice consequence about this identity is that it tells you something about the spectrum of the Schrödinger operators, which you can already see in this picture here. So that is really the spectrum for a real, I mean, for a model of time reversal invariant topological insulator that takes the name of Kane-Mele model. And that is the spectrum in the non-trivial case in which you have, in which you have non-trivial edge transport that corresponds to the presence of these edge states here. So what you should notice by looking at this picture is that the picture is symmetric with respect to special points, which are the points that on the circle are left invariant by k that goes into minus k. So k equal to pi and k equal to 2 pi, these are left invariant. So that means that if you have an edge state, let's say that connects this tip of the cone to this other one, by flipping the picture, you need to have another edge state that meets exactly at pi. Okay, so that's really just because of the symmetry, because of this symmetry here, if you want. And the nice thing about that is that by the fermionicity of time reversal symmetry, this crossing of eigenvalues here, it needs to be even degenerate. So that's a theorem that takes the name of Kramer's theorem. This is telling you that whenever you have an eigenvalue at points that are symmetric with respect to time reversal symmetry, these eigenvalues have to be even degenerate. Okay, so that fact actually implies some topological stability of this picture, and this turns out to be actually, this actually turns out to imply a Z2 classification for Hamiltonians H defined on cylinders. So the Z2 invariant for edge Hamiltonian is actually equal, turns out to be equal to the parity of the number of pairs of edge modes at the Fermi level mu. Okay, so in this case we just have one pair of edge modes, and the parity would just be +1. So why is that a Z2 classification and not a Z classification? Well, think of having two crosses that, think of having the same picture, but now let's add another cross here. Well, what you can do, you can think of deforming the blue cross so to meet the red cross at this point, and then you have an eigenvalue that is fourfold degenerate, and you can split this fourfold degeneracy by ideally you can split it by two eigenvalues that are now twofold degenerate, so you don't violate Kramer's theorem, but once you have that, again, ideally you can think of pushing these curves in the bulk, and then you're left with a trivial insulator. So that's about edge transport. It turns out that also one can also define a bulk Z2 classification. That's not as easy as I did now, but and also it turns out that this Z2 classification apparently doesn't really have a direct connection with bulk transport properties. That's a bit in contrast with the quantum Hall effect, but still one can prove a duality between these two classifications, and that was that was done some years ago. All right. So that's about an overview for non-interacting systems. Now what I would like to do is to switch to interacting fermions, and in particular to interacting fermions on lattices. Okay, so I will make use, I will somehow, so the setting is very similar, actually, is very similar to what Manfred already introduced yesterday in his lecture. So, so what we have is so far a finite portion of Z2. Think about a finite square lattice with side L. And I want to look at many-body fermionic Hamiltonians that have the following form. Okay, so I will have in general a quadratic part, which is the so-called second quantization of the first quantized Hamiltonian H. And what is going to make the problem difficult is the presence of this other operator here, which is going to be a sum of quartic operators, quartic monomials in the fermions. Okay. So again, these are fermionic creation annihilation operators acting on the fermionic Fock space. They satisfy the usual canonical anti-commutation relations. And in what follows, I will always assume that, well, okay, I will make some assumptions on H and V later on, but I mean, what you should keep in mind for the moment is that both of them are going to be short range. So think of them, actually also exponential decay is fine, but if you want, you can just keep in mind that both h of x and y and bx minus y, they're actually short range in the distance between x and y. All right. So I would like to study this interacting model by, well, in the language of statistical mechanics. So that means let me introduce the usual finite temperature and finite volume Gibbs state. Beta is the inverse temperature and mu is the chemical potential that fixes the average density. Okay. So now, before telling you about, well, edge transport properties, let me tell you something about bulk transport. Okay. So let me consider first the case of periodic boundary conditions. Okay, so there is no edge, and I want to have periodic boundary conditions in both directions, and at the end take the volume as L goes to infinity. So it turns out that also in this many-body setting, one can define Kubo formula for the conductivity matrix again by just doing a formal Duhamel expansion as a function of the external electromagnetic field. And if you do it, what you get is the expression that you see here. So you should, there are some things one should notice in this formula. There is a time integration from minus infinity to 0. That means that I want to introduce an external field at the time t equal to minus infinity, and I want to make the measurement at 0. And I want to do that slowly. So that means that, well, in particular, I can do that by introducing this adiabatic parameter e to the eta t. Okay, so eta is a positive number, and this depresses the external field exponentially in the past. So L is the size of the side of our square lattice. Think about a square lattice for simplicity. And J is the current operator. So it is really just the derivative of the second quantization of the position operator. Okay? So that is the many-body version of Kubo formula, and it turns out that one can prove that, that the transverse conductivity that defined as follows is actually quantized as in the non-interacting setting. That was actually a recent work of Hastings and Michalakis. They proved quantization of the whole conductivity by, well, by assuming that the interacting ground state of the Hamiltonian H is separated by the rest of the spectrum by a positive gap. Okay? Now, using a completely different strategy in collaboration with Alessandro Giuliani and Vieri Mastropietro, what we did is to give another proof of this fact by actually showing that this conductivity matrix defined here is universal. Okay, so it doesn't depend on deformations of, you can introduce deformations of your many-body Hamiltonian that include, well, many-body interactions. And provided the deformation is not too large, what you can prove is that this object here is actually universal, so it doesn't change its value along the deformation. So in particular, you can prove quantization of the transverse conductivity by showing that sigma 1,2 is constant with respect to the many-body interaction. And with respect to the previous result, what we actually assume is, well, we don't really need the presence of a gap. At the end, the proof only really requires some fast enough algebraic decay of correlations, which of course is true if you have gapped ground states, but you can also push it to some other graphene-like settings if you want. Now, okay, so this is about quantization of the transverse conductivity. Now, there is another problem, which is in a sense complementary, which is about establishing the validity of this expression starting from many-body quantum dynamics, and that again is something that has been understood recently in the setting of non-interacting fermions. That is this recent work of Bachmann, de Roock, and Frass, where they proved an adiabatic theorem for many-body quantum systems, and as a consequence of this adiabatic theorem, they proved the validity of Kubo formula for gapped ground states. Okay, so that's about bulk transport, but what I would like to focus on today is edge transport. So let me introduce the relevant setting to probe edge currents. So let me go back to my cylinder, think about this side to be identified with this one, and think about having Dirichlet boundary conditions here and here. And think about looking at, physical observables that are supported in this red region. Okay, so I would like to have I would like to probe the response of physical observables that are confined in this red region here, where the width of this rectangle is defined to be this calligraphic L. Okay, so at the end I will take big L to infinity, and then I will take small L to infinity. Now, when I mention, when I talk about interesting physical quantities, well, what I really mean is that I would like to look at the charge density, which is an operator in Fock space. This counts how many fermions you have on a given site X. And the other operator I will focus on is the current density, which is, well, which is the operator that satisfies the lattice continuity equation. Okay? So, so these are the two quantities I will consider, and I also need, in the following I will need a little bit more notation. So let me introduce this partial Fourier transform n hat of P1. That just means that I'm taking the Fourier transform in this direction here, and I'm summing over all lattice sites in this direction here. Okay, so you just have a non-trivial phase factor for this coordinate x1. And then I also want to introduce the same quantity but decorated by this calligraphic L. That just means that you take this definition and you truncate the sum over x2 over this red region. All right. So that's about charge transport. Of course, you can also think about spin transport if you want, and to do that, it is convenient to assume that, that the full Hamiltonian commutes with the spin, let's say with the third component of the spin operator. The reason is that if that is true, you can actually, well, you can talk about a continuity equation for the spin current and for the spin density, which, well, which is in a sense trivially related to this one, right? So the spin density is just the difference of the spin densities with opposite spins, and if you have this property here, the current density is just going to, the spin current density is going to be given by the difference of the currents with the opposite spins. Okay. So that's about the setting. Now, what are the transport coefficients I would like to look at? Well, they are defined in this slide. So let me go through that. So the first one is the edge charge susceptibility, which tells you about the response of the edge density localized in this red region with respect to perturbations that couple to the density all over the lattice. And again, I want to take, these are definitions. You can motivate these definitions by doing formally one step of Duhamel expansion for the average of the density. Now the second definition is about the edge charge conductance. You look at the variation of the current of the average of the current once you couple a perturbation with the density over the whole lattice. And finally, the last edge transport coefficient is the edge Drude weight, which tells you about the response of the current operator located close to one of the two edges once you couple the system to an external electric field all over the lattice. Okay, so these are the quantities I would like to study, and now before telling you what we can say about those, let me tell you what what would a physically reasonable effective model to look at to study these edge transport problems. So suppose that you have, for simplicity, just one edge state per edge. Okay, so in the previous picture, you remember you had these curves that connect the two bands. Suppose that you just have one curve that connects the two gray bands, and forget about the other one on the other lattice. So it turns out that the transport properties of your, the edge transport property of your system can be effectively described by the Chiral-Lattinger model, which is, which is a model for 1 + 1 dimensional fermions with a relativistic dispersion relation. Okay, so here I'm assuming that the velocity of the fermions is given by VE. I don't have two branches, I just have one branch, which has a certain sign, which is specified by the electric, by the VE parameter. Okay, so that is a model for a relativistic 1 + 1 dimensional fermionic particles, and this model is actually a central model for a theory of edge transport that was introduced by Wen at the beginning of the 90s, which in fact allows to make predictions about the edge transport coefficients on the basis of approximating edge transport by the Chiral-Lattinger model. And the reason why this is a good idea is that this Chiral-Lattinger model is actually an exactly solvable model by bosonization techniques. Okay. So that's one effective model. The other effective model is an effective model for time reversal invariant system. That's the helical Lattinger model. And here what you assume is that you have two families of fermions with opposite velocities, and the velocities are somehow now locked with the spin. So if you have a given spin, the velocity is positive. If you have the opposite spin, the velocity just changes sign. Okay. Again, also this model is can be solved by bosonization, and the remark here is that integrability is non-generic. So as soon as you introduce perturbations, let's say you replace the linear dispersion relation by a nonlinear one, or you include bulk degrees of freedom, then you just lose all the integrability properties of your quantum system. Okay, so what is the theorem? That's a joint work with Giovanni Antinucci and Vieri Mastropietro. So this is a statement about what happens if you consider Hamiltonians H that defined on the cylinder that display one edge state per edge, like in the picture I showed you before. So what one can do here is that, well, the first part of the theorem is about making sense of the Gibbs state as a function of the many-body interaction. But the interesting part about it is, the most interesting part is about the prediction for the edge transport coefficients, which you see in these three lines. Okay, so forget for the moment about these error terms and just focus on these explicit parts. So what this is telling you is that the edge transport coefficients are given by explicit functions as a function of momentum and the adiabatic parameter. And the nice thing about it is that all the dependence on the many-body interaction is encoded in this parameter V, which plays the role of dressed Fermi velocity. Okay, so this is an error term, and the reason why, what one can prove is that this error term actually vanishes whenever you take momenta to 0 and you take to infinity the size of the strip where the observables are localized. So, okay, so that is nice because you see these three nice functions here are actually what you would get from, by studying these effective models I gave you before using bosonization methods. And in particular, you notice that these expressions are just the derivatives of correlation functions for a non-interacting one-dimensional Bose gas. Okay, so this really recovers the prediction of bosonization, and the proof is based on renormalization group methods and on a rigorous comparison with the chiral Lattinger liquid following ideas that have been introduced by Benfatto, Falco, Mastropietro starting from 2010. Okay, so that's the result. Now, what are consequences of this theorem? Well, the first is that if you now look at the zero momentum limit and an infinite strip limit for the edge conductance G, what you see is that, you just take this quantity here, omega is the chirality of the non-interacting edge mode, and what you see is that if you send eta to 0 and then p to 0, all the interaction correction just disappear because you get a ratio of VP1 with VP1, so that is just 1. Okay, so in this sense, you recover the universality of the edge conductance by, this is exactly what you would have in the non-interacting theory, so by the non-interacting bulk edge duality, you know that this is equal to the transverse Hall conductivity, and again by the stability of the, by the essentially the quantization of the Hall conductivity for non-interacting system, you can lift the bulk edge duality from the non-interacting system, from the non-interacting world to the interacting world, again by using universality. So that's about that's about this G transport coefficient. Now, what about the other two transport coefficients that I defined before? Well, it turns out that these guys are not universal in general. So if you take the zero momentum limit, you still get a non-trivial function of the many-body interaction. But you get special functions. So you get this nice structure where V appears at the numerator for D and at the denominator for K, for kappa. And this relation is exactly what was predicted to hold true by Haldane at the beginning of the 80s in his theory of Lattinger liquid theory of one-dimensional systems. So what you get is that the ratio of the Drude weight and the susceptibility is equal to the Fermi velocity squared, which is what is called the Haldane relation for one-dimensional quantum systems. Okay. Good. So that's about charge transport. Now let me talk about spin transport, and that is joint work with Vieri Mastropietro. So again, what we want to do here is to look at many-body perturbations of single particle Hamiltonians H that display one pair of edge modes at the Fermi level. So what I have now is that on every edge I have this cross that I showed you before corresponding to counter-propagating edge modes. And also, I will assume that the many-body Hamiltonian commutes with the third component of the spin operator. That is because I want to have a well-defined current, spin current. Okay, so that does not mean that H is the sum of two Hamiltonians with opposite spins. So the theorem is not just a trivial consequence of the previous one. You might have that the many-body interaction couples the spin. So in this setting, one can prove again universality of the edge spin conductance, and that is expressed by this identity here. It only depends on the chirality of one edge mode. And okay, as before, you can also compute all the other transport coefficients, namely the edge Drude weights and susceptibilities, charge Drude weights, and the spin Drude weights and susceptibilities. Okay, so you get a structure that looks a little bit more complicated than before. Again, you have this non-universal Fermi velocity, and also you get this K parameter here, capital K, which was equal to 1 before, and now it's just it's given in general by a convergent series in the many-body interaction. So this is these are the expression for the transport coefficients. It turns out that this K parameter is also called the Lattinger parameter. This is related to the anomalous exponent of the two-point correlation function eta by this relation here. And in the previous case, this K would just equal to 1. Okay, so that's these are the results. Now let me tell you something about the proof of these theorems. Let me focus for simplicity on the case of one edge. Yes.
K is related to the bosonization
Yeah.
in the non-interacting setting. Here it is interacting, but in the large scale limit, do you still find this bosonic limit?
Yeah. I mean, these are exactly the predictions of bosonization. But the point about it is
Endpoint functions are a product of 2-point functions. I mean.
Yeah, so we didn't, so we did not, so I believe this to be true, but we didn't prove it. So I mean, we have a, you know, statement about construction of the Gibbs state and computation of this class of response functions. I believe that in general you can actually look at any current or density correlation functions and prove that in a certain scaling limit these are equal to those of a free Bose gas with renormalized parameters. But this we didn't prove in our paper. I believe, however, that it's true. Okay, so good. So that is that's what happens. And now, in the remaining part of the presentation, I would like to tell you something about the main ideas of the proof in the case of one-edge state that is simpler than the case of two-edge states. Okay. So the starting point is to well, understand how to deal with the fact that we have real times, because I mean, as we heard in Volker's talks yesterday, I mean, applying the renormalization group methods to real-time evolution is in general very hard. I mean, renormalization group is much better tailored if you wanted to study static correlation functions or Euclidean correlation function, namely imaginary time evolution. Now, in this case, the way out is given by a rigorous version of Wick rotation, which goes as follows. So consider the time integral of a suitable commutator of two local operators, A and B, and introduce an adiabatic parameter which is now dependent on beta, and it's actually what is called the Matsubara frequency. Okay, so what you can see here, just by really standard complex analysis, is that well, you take this commutator, you open it as a difference of two terms. The first term, the AB term, corresponds to an integral here. The other term, which is of the form BA, can actually be casted back in the AB form by shifting in the imaginary direction of time. So that's what is called the KMS condition. So you can use cyclicity of the trace if you want in the state, but if you do that, one of the two, the time variable will become shifted by an imaginary time quantity minus I beta. Okay, and it is crucial that this exponential factor has this form if you want to have the same function here and here. Okay, so in this way, the difference of terms appearing in the commutator corresponds to an integral here and an integral here on these two sides of the rectangle. Now, by analyticity, you know that the integral over the loop is 0, so you can trade these two integrals by the integral here, which is what you want to have at the end. So that's a Fourier transform of a Euclidean correlation function plus an error term. That's this dotted guy. And the nice thing about this dotted guy is that it lives on times which have a huge negative real part. Okay, so I'm writing this identity for a fixed large negative time t, and if you do that, you get an error term which lives on this dotted line, which is penalized by an exponential of minus t eta beta. Okay, so that is nice. Of course, that's not enough, because you also have to be able to control the integration here if you want to have a result uniform in beta. You have complex time correlation functions, but by clever use of Cauchy-Schwarz inequality, you can actually estimate complex time correlation functions by Euclidean correlation functions, and that's how you do to prove that this error term is actually vanishing as t goes to infinity. Okay, so in this way you get this nice identity with this discrete family of adiabatic parameters. They depend on beta, and if you have a general adiabatic parameter, you can approximate it, of course, by the closest eta beta. Okay, so it is crucial in this setting that you first take beta to infinity and then eta to 0. In the opposite, if you do the opposite limit, then all of this, of course, this approximation argument will not be very useful. Good, so the starting point is now, it's a Fourier transform of a Euclidean correlation function that, I want to shift the integration now and introduce this time ordering t. And the nice thing why this is nice is that, of course, you can study these objects if you want by doing perturbation theory. You expand the Gibbs state with respect to the non-interacting Gibbs state, and you get a series of cumulants in the many-body interaction, or rather, imaginary time evolution of the many-body interaction. That's the notation you see here. So that is somehow nice. You can expand all these cumulants in terms of Feynman diagrams. The basic ingredient of the Feynman diagram is the two-point function, which can be computed starting from the single particle Hamiltonian H, and you get a very nice explicit expression. So, of course, I don't need to explain that to this audience. This is way too naive, for two reasons. The first one is that you have way too many Feynman diagrams. You have 2n factorial at the order n. And the other reason is that in this case, whenever you don't have a gap, this two-point function just decays too slowly to just even prove that a single Feynman diagram is finite. So you have to be more clever, and the starting point is to introduce a Grassmann integral representation of the theory. Let me just focus on the partition function via this identity. And here, I mean, as usual, I have a fermionic Gaussian integration. So psi, these are Grassmann variables, as we heard yesterday in Manfred's talk. And the covariance of this Gaussian Grassmann measure is given by the non-interacting two-point function of the model. Okay, so this V psi is a quartic interaction. Think of it as psi to the 4, I mean, a local interaction if you want. Having some no locality doesn't really make a difference at the end. All right, so what do you do next? Well, you take your Grassmann field and you split it as a sum of two. One is a Grassmann field that depends on all bulk degrees of freedom. So you artificially introduce a gap at the Fermi level by separating the energy modes close to the Fermi level from those that are away from it at a certain fixed distance delta. So this guy here would decay exponentially. Okay, so if the theory would only contain this propagator, you would have exponential decay of correlations, and it would be, of course, much easier. So, right, so you use the addition principle of Grassmann variables, Gaussian variables, to split the Gaussian integration in two, and you expand the many-body interaction, just you expand the exponential and integrate with respect to the massive field, and in this way you end up with an effective theory that only depends on the edge field. So, of course, the expansion, again, you would have the 2n factorial problem, as I mentioned before, but you don't have to expand in Feynman diagrams, as we learned from, pioneers in the field. You have to expand in terms of trees. Okay, so I mean, all loops that takes place in Feynman diagrams, these are those that give this proliferation of, that they give you at the end this 2n factorial problem. You can actually pack all these loops into suitable, I mean, you can decorate these trees by determinants, and these determinants allow to take into account all loops. Okay, so that's a very nice properties of fermion, and the reason why this is nice is that, of course, trees at a given order are much less than the Feynman diagrams. You get just an n factorial, and the determinants can be estimated in a much more efficient way than just counting the number of entries in the Leibniz formula for the determinant. Okay, so that's how you integrate the bulk degrees of freedom, but then, of course, you are left with the hard part of the problem, which is to integrate the edge field. And the observation here is that the edge field, which only depends on what happens at the Fermi level or close to the Fermi level, it only depends on the branch of eigenvalues that intersects the Fermi level. This edge field close to the Fermi level, when you take the Fourier transform with respect to the one direction, can actually be represented as the product of a truly one-dimensional field phi times the edge state eigenfunction psi. Okay, so this guy here contains all the dependence on the second variable, which is the one where you don't have translation invariance, but you have exponential decay due to the edge states. Okay, so that's a nice representation, and this guy here now, I mean, basically the sum of the dependence on the second variable is decoupled, so you can sum over all second variables, and you get a theory that only depends on this effective one-dimensional field. All right, so this is a massless one-dimensional field whose covariance, whose covariance is here. This is the edge state dispersion relation, and close to the Fermi point, which is the value of k1 that such that epsilon k1 is equal to mu, you get this linear dispersion relation in terms of some Fermi velocity v. Okay, so that's how you see the chiral Attinger liquid arising from this, if you want, two-step multi-scale integration so far. All right, so now you want to integrate this Grassmann integral, and to do that, you cannot do it in a single step, you have to do it in a multi-scale fashion, and that's the rigorous renormalization group for fermions that was developed by many people in the last 30 years. So you take your fermionic field phi, you sum it, you write it as a sum of independent fields living on given energy scales, starting from the smallest scale, which is fixed by the inverse temperature beta, so you have a finite number of scales, and then on every scale your field phi of h is essentially supported for momenta that have that correspond to a certain energy, 2 to the h. Okay, so h is a negative number, you're getting, as h gets negative and negative, you're getting closer and closer to the singularity at 0. Okay, so the covariance of this field is this g hat of k, which is basically what you see here once you decorate it with a cutoff function that tells you that you have to stay close to the singularity at a given distance 2 to the h. Okay, so you integrate these fields in an iterative way, you get an effective, sequence of effective integration measures and effective actions, and the point is to control these discrete dynamical systems. Giving you the new integration measure and the new effective action. Let me just focus on the problem of controlling the quartic interaction. So for the quartic interaction, what you get up to irrelevant terms is, it's a local term where well, you just have a local interaction in coordinate space. Of course, now it's crucial that you have the spin, otherwise you cannot make that without having, by Pauli that would be just 0. But if you have the spin, that is not 0. And this is weighted by a marginal parameter, lambda h, which satisfies the following recursive equation where beta is the beta function of the RG. Okay, so that is a marginal coupling. That means that if you just naively estimate this by, you don't even try to evaluate the second order, but you just estimate it, what you get is an estimate that doesn't allow you to iterate. I mean, it just blows up. So you have to do something better, and something better means exploiting the emergent integrability of the chiral Lattinger model. Okay, so you take your beta function, you write it as a sum of 2. This is a beta function of a suitable chiral Lattinger model with parameters chosen so that the correlations at large distances match the correlations of the Lattinger model. And you have then some small correction which takes into account all nonlinearities of the energy bands. So the nice thing about this small correction is that it is really small. I mean, it comes with a summable factor 2 to the h, where h is negative. So if you only had this guy here, you would have a summable iteration, and then you could prove analyticity uniform in temperature. But that's, I mean, okay, in general, you also have this guy here, but it turns out that this guy, because essentially of the integrability of the model, is exactly 0. Okay, so that's how you can prove analyticity uniformly in inverse temperature and system size. So, of course, this allows, this only allows to, in a sense, to construct the theory, but then you also want to prove universality for the transport coefficients of this model. So, how do you do that? Well, again, the starting point is to use renormalization to rewrite the lattice correlation functions in terms of the correlation functions of the chiral Lattinger model up to some renormalizations that in particular take into account the effect of the second variable. Okay, so these are exponentially decreasing function because of the exponential decay of the edge states. And then you have small errors that come essentially because of the presence of the bulk degrees of freedom. But these you can really in a sense forget. I mean, okay, you cannot neglect them, but they are subleading with respect to this explicit term. Okay, so the nice thing about that is that these correlations, again, these are the correlations of an exactly solvable model, so you can compute them explicitly, and you get a nice explicit dependence on the momenta, on frequency and momenta, but you get a bunch of parameters that are there so that you can match this chiral Lattinger model with the full lattice model. So, okay, maybe instead of, okay, so you have a bunch of parameters, you have a renormalized Fermi velocity, you have a wave function renormalization. This tau parameter is related to what is called the anomaly in this 1 + 1 dimensional theory, and maybe it can be understood via this graphical identity for the density-density correlation function of the chiral Lattinger model. Okay, so this, I mean, if you would have formally a 1 + 1 dimensional theory with no ultraviolet cutoff, you would have, you would have formally that essentially the density-density correlation function is exactly 0. I mean, you would have a 0 right-hand side. But the point is that you have to regularize this relativistic theory with an ultraviolet cutoff. If you do that, you spoil gauge invariance, and what you get is that if you write down the continuity equation for the density-density correlation function, you get error terms that depend on this ultraviolet cutoff. So this circle here is a new vertex that you have in your theory, whose effect is to localize the outgoing line and incoming line on the scale of the ultraviolet cutoff. Okay, so this, I mean, if you have the ultraviolet cutoff is very far in the ultraviolet, but nevertheless, it has a non-trivial effect because this bubble diagram, they scale exactly. So they are there, they're non-zero, they're not going to vanish if you remove this and to infinity. But nevertheless, you can compute these guys explicitly, and you can prove that this term, which is the term where these two fermionic lines do not meet in the same point, as we have seen in Alessandro's lecture last week, this term is exactly 0 as n goes to infinity. So you get a nice closed equation for the density-density correlation function that you can solve, and if you do solve it, you get the identity that I showed you here. Okay, so that's how you can compute these objects. Now you want to prove universality. That means that you want to show that all these non-universal parameters essentially cancel out when you look at edge transport coefficients. Okay, so that seems to be a hopeless task, just because, if you just try to look at these guys in perturbation theory, it's extremely difficult to find a cancellation at all orders. So you have to find a mechanism for that to be true. And this mechanism follows by, it turns out to be implied by word identity. So continuity, conservation laws for the lattice model and for the emergent relativistic model. So let me just give you an idea of this conservation, of the use of these conservation laws for the vertex function. Okay, so let me denote by let me denote the states of these two models in the usual way. So that's a lattice model, that's a relativistic model. And then you can write down the word identities for the vertex functions of the lattice model. That's what you see here. That's a consequence of the continuity of the lattice current, of the conservation of the lattice current. And then you have a word identity also for the relativistic model, which is, however, now different essentially because of the presence of this tau parameter. That's again the anomaly. Okay, so these are two nice identities. How do you use those? Well, the point is that you want to use again renormalization to show that the lattice correlation functions can be expressed at large distances as the correlation functions of the relativistic model up to some renormalized coefficients. Okay, so this is the connection between these two identities. You see, you take the first one, you use again renormalization to prove that at large distances the correlations of the lattice model look like the correlation of the relativistic model up to some non-trivial renormalizations. But then once you have that, you basically have two equations for the same quantities. Okay, so you have two equations for the same quantities. If you combine them in a clever way, you see that the only way in which these equations can be true is by having non-trivial identities between all these non-universal parameters. Okay, so this is ultimately what implies universality of the edge conductance. Now, okay, so let me conclude. So what I presented today are results for edge transport coefficients for two-dimensional topological insulators with either single mode edge currents, which are relevant for quantum Hall systems, or time reversal invariant systems where every edge comes with a pair of counter-propagating edge modes. Now, consequences of our theorems are the stability of the bulk edge correspondence for interacting fermions and the validity of these Haldane relations relating Drude weights and susceptibilities. So the proof is based on renormalization and word identities, and okay, there are many problems that it would be nice to study. A very natural one is to understand how to extend all of that to the case of a general configuration of edge modes. Now, the reason why this is difficult is that if you have a general configuration of edge modes, you might have scattering between all possible edge states, and some of these scatterings are not going to be bosonizable. Okay, so essentially they will break integrability in a very bad way. Okay, so you have to deal with these new marginal couplings due to the scattering of different edge modes, and maybe what you can hope to exploit is infrared asymptotic freedom for a given sign of the coupling constant, but this has to be checked. Another very interesting problem, which is somehow dual to what I discussed, is about proving the validity of linear response theory for these edge transport coefficients, already in the case of non-interacting fermions. And this turns out to be a difficult problem because, well, we have a very poor understanding of adiabatic theory if you don't have a gap, and these are gapless systems. And finally, of course, perhaps the most ambitious problem is to try to understand how to use this rigorous renormalization scheme to say something about fractionalization of conductivities. Okay, so that's the end of my presentation, and I thank you for your attention.
Questions, comments? Okay.
When you showed us this renormalization group step, I mean, close to the Fermi surface, you showed how the quartic interaction renormalizes. Would this also, if you start with non-local quartic terms, reduce to this local Hubbard type interaction?
Yes. I mean, actually, our theorem is about, in general, we allow for non-local interactions, which, I mean, think of those as being exponentially decreasing. Of course, if you start to include some long-range interactions, then the scaling changes, and then I don't know how. But if it is a nice interaction with nice integrability properties, the effective, I mean, again, at small scales, you will only see large scales, infrared scales, you will only see a local interaction, basically.
Does the sign of lambda play a role here?
No, it does not, because we use this, in this case it does not, because of this vanishing of the beta function. So that is, of course, again, if you have a general configuration of edge modes, then it will, I mean, if you don't have the vanishing of the beta function, the only thing you can hope is to exploit the sign,
Maybe just for clarification, you introduced these by definition, these response functions by the Kubo formulas. So can you justify them in all these cases?
No. So these edge transport coefficients, even in the non-interacting case, as far as I know, there is no theorem justifying them. So it is what you get if you do a formal dual expansion, but of course, I mean, the current adiabatic techniques are not, we just don't apply to these cases. So I talked to the experts and they all don't know how to justify those. Yeah.
Following up on this, is what you discuss is this DC property?
So let's see, it depends. In some cases, you see, actually I didn't comment too much on that. So I have expressions for my transport coefficients at fixed adiabatic parameter and fixed momentum. And then you get a non-trivial result depending on how you take those limits. So for some of these transport coefficients, if you take them in a certain order, you get something non-trivial. In the other order, you just get 0. So in particular, the edge conductance, you get a non-trivial result if you first send to 0 the adiabatic parameter. That means it's a static in time perturbation, and then send to 0 the spatial modulation. But for, let's say, the Drude weight, you have to do the opposite. And so we see that as a you know, something coming out of the computations. So in some cases, we're doing DC, and some other case, I would say we're doing AC, probably.
Yeah. So what are you going to do when you don't have the luxury of having a Luttinger model to bail you out of the beta?
Yeah. So what I hope is that well, if you don't have the Luttinger model as a, you know, if you're not in the Luttinger liquid, let's say universality class in that sense, what I hope is to well, okay, you will have other marginal couplings between edge states. What I would hope to use is infrared asymptotic freedom. So you will have a non-zero beta function in general, and for a sign of the coupling constant.
So it will actually become irrelevant.
Yeah, exactly, marginally relevant. I think now, okay, so if I understand correctly the physics literature, that is not just a technical point. I guess this sort of unclap scattering, they are expected to open a gap, actually, if you choose the other sign. So actually that could even be related to fractionalization of the whole conductivity. It might be, but yeah. But then it's an interesting question to try to construct that, at least in the asymptotically free case. Yeah.
So if you introduce another parameter, maybe the number of components of the Fermi field, so you can do 1 upon n.
Yes.
You could get a non-Gauss. I mean, you might be in a situation where the beta function is controllable because it always remains small.
Yeah, I didn't think about that. It's a very good, thanks. That's a very good remark. So having a large number of components for a Fermi field, it actually corresponds to having a large number of edge states. I mean, in a sense, these are related to internal degrees of freedom. So yeah, it could be that in the case in which you have many of those, maybe you can exploit some 1 over n expansion. Yeah, I didn't think about that, but that could be, that could be a nice thing to do. Yeah.
It's a hard problem for the Bose problem to introduce the 1 upon n expansion. It might be easier for fermions.
Yeah, thanks. Yeah, that's.
It works to the Gross-Nadeau model.
Yeah, yeah, nice. Thanks.
I see no further questions. Well, thank you very much again.
Thanks.